So let's derive this T loss expression which we just saw. The aim is to determine the speed of the liquid coming out over here as it leaves the hole when the liquid's level is at a distance h above the hole. So we have the liquid exposed to this amount of water and the height is h. The proof starts with the standard assumption. Let's consider an enclosed tank containing a liquid of density rho has a hole in its side at a distance y1 from the tank's bottom. So this is y1. It's not enclosed, this is open. I opened it actually before it was enclosed, but I'm opening it. The hole is open to the atmosphere, right? This is open to the atmosphere. And its diameter is much smaller than the diameter of the tank. So the diameter over here is much bigger to this. The air above the liquid is maintained at a pressure of P. So I kept it open, so it has to be at a pressure of PA, atmospheric pressure. Okay guys, now we are going to make use of two things. Just a second. So first is as per equation of continuity. This is the first thing that we'll use, and the second thing is Bernoulli's principle, the equation. So we know that A1 V1 has to be equal to A2 V2. Sorry, this is supposed to be small v. Yeah, I think that's better. So V2 will be equal to A1 by A2 times of V1. Simple math. Now, what is this A1, V1 and all of that? A1 for me is over here, A2 is over here, V1 will be over here. V2 is over here. That is, V2 is at what rate the water is reducing in the tank. See, most of the time what we're dealing with is huge tank and a small hole. So the area, the cross-sectional area over here is way bigger than A2 is much bigger than A1. If this is the case, what will happen to this ratio? This is almost equal to 0. So what can we tell? As we have A2 much greater than A1, the liquid may be a liquid drop actually, not maybe, liquid may be, okay, let me just continue with this, taken at rest at the top. So that is V2 is closer to 0. So the rate at which this is falling is almost nil. You won't be able to notice it, at least for a fraction of a minute or a second. It won't make a difference. If you just observe it for a second, you won't get to know that water is dropping. That's what I mean. Now let's apply Bernoulli's equation. So this is actually, okay, technically this is not yet complete, at point 1 and 2. 1 is the small hole, 2 is your top. So P1 plus rho, this is your kinetic energy, and this is your potential energy. This has to be equal to pressure, kinetic energy and potential energy. Okay, then we need an expression for V1. So a bit of rearrangement. Half rho. Oh yeah, first thing is, let's substitute it off. Substituting V2 which is almost equal to 0. So this will go to 0. And this and this will get cancelled actually. So let me not write all of that. So this is 0 meter per second. Then we have P1 is equal to P2. Both are exposed to atmosphere. So this is PA, right? So this is pushing with pressure of atmospheric pressure of PA. This is also pushing with atmospheric pressure of PA. Tank is way smaller than the atmosphere. So this height difference H, it's negligible when it comes to atmosphere per se, right? So both are exposed to the same pressure, and that is atmospheric pressure. So if I do substitute all of this, what will happen? P1 and P2 gets cancelled. I'm not going to write all of that. So all this substitution and vagera, you guys can handle it, guys. Because you are not small kids anymore. So what will get cancelled? You have rho G y2 minus y1 is the only thing that is left out. So rho and rho will get cancelled. And y2 minus y1 is your height difference. Okay. y2 minus y1 difference is h. And so we have v1 is equal to 2gh root. And that's that. This is not technically needed because I kept the tank open. A very simple derivation.